Hello, my name is Sean. I study at World Earth for Silver, and I'm going to talk about time dilation. Time dilation is a phenomena where the faster you move, the slower time passes for you. Now, a basic example of that is a spaceship. If you travel on a spaceship, for example, for 2 years, and say this spaceship is really fast, for example, half the speed of light, the time that passed for you when you come back would be less than the time that passed on Earth. So, for example, you would have aged 2 years on this journey, and people on Earth would have aged maybe 3 years, maybe a bit less. So this phenomenon isn't it's not something we feel every day, but it's very important in a lot of fields. And we're going to discuss how people got to it and why it happens. Okay, so the first thing that we need to understand this phenomenon is to have an idea of what classical relativity is. Okay, so basically what classical relativity says that if you measure the speed of another object, depending on your speed, the object's speed will change. So a basic example is you're driving in a car at a speed of 10 kilometers per hour, a constant speed, and you see another car driving at 20 kilometers per hour. Now, when you measure the other car's speed, it would seem as though the other car is moving at 10 kilometers per hour, because it's the difference between the two cars' speeds. And if the two cars drive at the same speed, when either car measures the other's speed, it would seem as though the cars aren't moving. Okay, so now I understand classical relativity. There is a problem with it, and that is light. Apparently, however you measure light, doesn't matter what speed you're moving, you always get the same constant speed of 300,000 kilometers per second. Now, this doesn't make sense according to classical relativity, but Einstein proposed a solution which says maybe the faster you're moving, time slows down for you, and that will account for the speed of light staying constant. Now there is a very classical experiment that proves this theory. Basically you have two mirrors, and you have a light beam going up and down between the mirrors, and you can treat this as a clock. Basically every time the light beam hits the lower mirror, one tick passes. Now you have two situations here. One where the two mirrors are stationary, and one where the two mirrors are moving at a constant speed. Now, you see when the mirrors are moving at a constant speed, the distance the light needs to travel to get back to the first mirror is a lot longer. So, in other words, it means one tick in this clock would take longer than one tick in this clock. Now, of course, there is also a mathematical proof. It's not very complicated. There is a bit of use of Pythagorean theorem and some basic kinematics. And in the end, you get this equation, which creates a relativity between the time you experience when you're moving at a certain speed relative to the speed of light to the time a stationary observer experiences. Okay, now that we understand the classic explanation, there is another explanation that I'd like to give you, which hopefully will help you understand this better. Now imagine a car driving on a straight road towards the north. The car is going at a constant speed. We have a graph here which describes the north and the east. So the car would go something like this. Now, at this situation, obviously the car is advancing only to the north, and because it's going at a constant speed, every time period the car advances the same amount. Now, if we change the road a bit to go to the northeast, some of the work of the car would go to the east as well as the north. So now every time period, the car would not only advance to the north, it would also advance to the east, which means it will advance less to the north. Now, we can do something very similar with space and time if we just change the graph a bit, and instead of the east we write space, and instead of the north we write time, and just reset it. So obviously we're always moving through time, so that would be the equivalent of only moving to the north in the car. And when we start moving through space or any kind of movement, it will be the equivalent of starting to move to the east in the car, which means we start moving less through time, which means time passes slower for us. Okay, so you might have noticed in your everyday life that when you're driving in a car, time doesn't move slowly for you. Well, the thing is, this effect happens, well, it does happen, but the amount is very unnoticeable. But it is useful. For example, something which is very useful to us, satellites, they provide us with a lot of services like GPS and television. They move around the Earth in very, very high speeds. So that means time passes for them slower than it does for us. So for example, a GPS satellite, which needs to send a signal to your phone every specific amount of time relative to you, can do that exactly because time passes slower for it. So it has a built-in system which calculates according to this equation and maybe a bit more physics, but it's all based on this. It makes a calculation that adjusts for how much slower time passes for the satellite, and then it can send signals in exact intervals to your phone. Thank you for watching, and I hope I helped you understand time dilation, and I hope you learned something new here. Yeah, thank you.